A quick recap from last time. Uh, we saw that everything in deep learning is about tensors and scalars and matrices and matrix multiplication and basically matrix manipulation and linear algebra. And that's why we spent the whole sessions last time on talking about different things in linear algebra. What we are going to do today is spending 3 hours on eigenvalues. No, I'm joking. So for eigenvalues, I saw that Willy posted a very good YouTube video in the channel. If you haven't seen it, go watch it for 17 minutes. You learn everything that that I couldn't teach you last time. So so good news is that we are not going to need any eigenvalues for this session. If we need it in the future session, we will make sure that we will again review that to make sure you have everything you need for that session. All right. So today we are going to have a lot of fun with something very interesting and useful. So we are going to talk about convolutional neural networks, not the network itself, but the math behind it. Because remember, we are going to, this is about the math in machine learning, in deep learning. And we will talk about what is the convolution. And for people who are coming from different angles into deep learning, convolution is one of those concepts that they have to deal with. But if you don't get it right, you will end up using it as a layer, and you ignore everything, and then things become mysterious to you. So we want to demystify that. And what is convolution? What is a kernel? What does it do? And then we will talk about one-dimensional convolutions. We will do hands-on in Python so that you see and experience and learn how convolutions work. And we will do it in PyTorch as well. And then we will do two-dimensional on images. You will, in the hands-on sessions, you will use convolutions to detect edges and use it to detect veins in biomedical images. All right? So that's the first step towards image segmentation, and you will see how convolutions are actually used in real life. And then we will talk about convolutional neural networks, and we will talk about all those words and concepts that you need to know to understand what is going on. So pooling, strides, dilation, and everything else. And in the end, we will talk about dropout. What is it? How does it help us? Why we need it? And so by the end of this session, I think you will be able to answer at least 5 interview questions when you interview for a data science job and they ask you, so we'll talk about it. All right. Why? Why do we need more than feed-forward multi-layer perceptrons? So we have seen that they work, and they are approximators to general functions. That's what we have seen in the last 2 sessions. But the problem is sometimes they need help. I mean, if we so if you look at deep learning as a black box, you take the black box, you throw data at it, and you don't give it any hints, and you say, go figure out the patterns and the relationships that I have in the data and make predictions. It tries to do that, but that's not the best we can do. What we can do is to take the data, extract information in ways that we will talk about, and then give that information to the system. And then we will see that we can be much more efficient if we do that, because we are actually helping the network. And in general, a convolutional neural network looks something like this. You have many layers, like pancakes, this way. And you have things that are called pooling layers. You have convolutional layers. You have stroids. You have dense layers and everything else. And we will talk about what each of these are and why they are useful. First of all, when we say convnet, that conv comes from convolution. What is a convolution? A convolution is, suppose you have, I lost my boundary here. Suppose you have two functions, f and g, all right? Convolution is something we do to these functions to tell us how one of these functions affect the shape of the other function. And the result is another function that has that information in it, okay? Pretty useless. What I defined, what it actually means is you have a function f and another function g. You take function g, and then you multiply, you compute f everywhere in your domain. You compute g everywhere in the domain, multiply them point by point, sum it up, and then you get one number. You keep that number, and then shift g by an amount, and then do the same thing. Multiply them point by point, and then sum them up. You get another number. Put it at the point where it tells you how much you shifted the function. If we look at images, it makes much better sense. So before looking at images, let's look at an example. Let's take the function f to be some arbitrary function, all right? And function g, let's take it to be the delta function. What is the property of the delta function? It's 0 everywhere. And it's infinity at one point. The other property is that if you sum it up over the whole range from minus infinity to plus infinity, gives you 1. All right? So the area below it is 1, but it's practically 0 everywhere. If I go back to the definition of convolution, and I apply it to this problem, so I get function f, and this is my function g, which is a delta function that I'm calculating it at a point. Now, what did we do? We said we take we take function g, we call it kernel. Okay, so kernel is that function, is the second function here, which we start sliding, and we slide it over all values of t from infinity, minus infinity to plus infinity, and then we take the integral for every at every point. All right, so the delta function is 0 everywhere except this point a, right? So I can take f out of the integral at point a, so that's f of a, and then I'm left with the integral of the delta function. What is this? What is the integral of the delta function? From minus infinity to infinity, that's 1, right? So that gives me this function f at point a. Now I start shifting it to different values. A goes from minus infinity to plus infinity, and that tells me that the result of convolving any function with the delta function is that function itself. If we see it, we understand it better. So this, I'll take function f to be a Gaussian. And this is what I do. I take f, and I start from infinity, minus infinity, and I start sliding it. So take it at one point and multiply it at every point. Multiply the value of the green function with the delta function. So it's 0 everywhere except that point where I have it here. So, and this is showing the result. That when I do that, I get a bunch of zeros when I multiply, except where they are overlapping, and that gives me the function itself. All right, so this is a visual way to look at it. Basically, you take two functions, you start sliding one of them, you multiply them, and then sum them up, and then you slide them and repeat. All right? To make sure that we don't have an eigenvalue experience again, we will look at a lot of examples here, and we will not move on until everyone understands this, okay? So let me know if you have any questions here. So let's repeat the convolution exercise with two top hat functions. All right? I'll start from here, and when I multiply, these are both. So here, they are 0. This one is 0. That one is not. But when you multiply them together, you get zeros, except when they start overlapping, right? So this is 0. You get nothing. Here you start getting values, and then it goes up and gets to the maximum, and then starts going down. All right? Does it make sense? You know what we are doing?
How you defined it at first,
yes.
at the beginning?
So here it is. You have two functions. All right? This function is, let's say, a top hat. This one is the second top hat function. And when you say t minus tau and t changes, that means you take the second function and you slide it from minus infinity to plus infinity. And at every point t, you multiply all of the functions point by point, and then you sum them up. All right, more examples. So this time, the top hat function, one of the top hat functions is bigger. The other one is smaller. So you see this is 0 all the way until they start overlapping. And as soon as they overlap, you start getting values. All right? And this is, so we are computing the value of the convolution at the position of this green line here. So this is 0. As soon as they overlap, the multiplication becomes non-zero because you have 1 here and 0.5 here, and then it starts going up. And when they completely overlap, you get a constant for here, because of the symmetry, you get a constant, and then when it starts moving out of the boundaries, the overlap becomes small, so this starts falling until they do not overlap anymore. So one of them becomes 0, and you multiply together.
So
yes.
Three functions in this.
Yes, because we have a function, a kernel, and the result of the convolution.
So all three needs to overlap.
The green is the result of convolving red with blue.
Okay.
So
Yes.
at negative 0.5, they haven't really overlapped. No, I mean negative 0.8.
Here?
Yeah.
Yes.
They haven't.
It does. So if you should look at where so we are computing the value of the convolution function at the point, yeah, at the line. Okay, so when the line gets here, they start overlapping. That's why it becomes non-zero, and then it starts increasing. Yes.
So the resulting function is a calculation of the area of the overlap, or what exactly?
Yes.
The area.
Yeah. So you multiply them together, and then you take the integral, which means the area under the two curves.
Blue function g is the blue sliding one?
This
no,
is
it's
G,
just
yes.
oh, g.
This is G. All right. One more, and this one actually you do this one hands-on in this hands-on session in a few minutes. So what it does, and this is starting to get interesting. What it does is that it takes, so we are taking a top hat function which has sharp edges, all right? And we are convolving it with a Gaussian function, which is smooth. And what it does to our top hat function is that it tapers off the edges and gives us this. So it rounds up the edges, all right? That has huge benefits. If you do anything in engineering, image processing, astrophysics, wherever you have sharp edges, you do convolution and you taper it off. It's very useful, and you will do it in a few minutes hands-on. So this one is useful to look at. The gray area is the multiplication of the two functions. All right, this is the multiplication of the two functions, and the green is the area under the curve for the gray area. All right?
Sorry,
Yes.
Can you just repeat the last part? The green is
So you got the gray one. Gray is when you multiply blue with red. And again, blue is called the kernel, and red is my function. You multiply them together, you get the gray curve. And to compute the convolution, you take the integral, which is the area under the curve, which is the area under the gray curve. All right? Yes.
So is the blue function always a delta function? Because this one, it looks different from the previous sliding function.
The function and the kernel, both of them can be anything. They can be any two functions. You can take you can take a cosine and convolve it with, what is your favorite function? With a linear function. Yeah, you can take any two functions and convolve them together. What it does is that it tells you how a linear function changes the shape of the cosine function if you convolve them together. All right? So, yes.
Can you just recap what is a kernel?
Yes. And please ask me questions as much as you want, because this is important. This is the core of everything we are going to do in the next 5 hours. So let's make sure that this is all very clear. The kernel is the function that you're multiplying with your function f. All right? So I have a function, all right? And this could be any function. I want to convolve it with a kernel to do something with it, all right? We will see that this kernel could be something that will help me taper off the edges, make it smooth, like what we saw. It could be a kernel that will help me denoise my signal, maybe my signal is noisy, I want to denoise it, all right? Maybe my signal is sparse, I want to bin it. So this could be a binning kernel. In 2 dimensions, I can have kernels that will help me find edges, and this is what you will do tonight, all right? So the kernel is a function that does something for us, and f is our image, our signal, our audio, our text, whatever our signal is, all right? So that's the function, and this is the operator. Okay, are you more comfortable with operator? Maybe we can say the operator and this the function or the kernel. These are all, people use all of these words. Yes?
So just if I can refer to the GIF we saw. So kernel there is the rectangular red function, right?
So the kernel, see, the kernel, you take G, you compute it at a point, all right? And then you take the integral, it gives you the convolution, the result of the convolution at point t, all right? And then you slide G to a new t, to a new value. And then again compute, and then multiply the 2 functions and take the integral. That gives you the value of the convolution at the new point, all right? So the thing that is sliding, the thing that is moving is your kernel.
Oh, I see.
The thing that is fixed is your signal. So here,
I can add something maybe to clarify. In these animations, the sliding is equivalent to increasing your T. So that's like each position is a T that, and you're increasing your T.
right.
Can fx or g of x be like a function that goes to infinity, like exponential function?
It can be, whether it is useful or not. Yeah. So it might diverge. You want a function that does not diverge when you multiply and take the integral. So, but in principle, it can be anything. F and G can be anything. Now, for the rest of our session, we will see how you pick your kernels to be something useful that does something for you that you want on your signal. Yes?
Okay, so I think of G as sort of a feature extractor. And you mentioned earlier that one of the reasons you do convolutions is to make the process more efficient, because it's less computation than if you just took everything from the signal. We're just going to take a subset that the feature extractor gives us.
Yep.
But then when I look at this diagram, the resulting curve, it is smaller than the others, which is what I would expect. But it seems like there's a scale issue, because if I had a 2 by 2 square or something, the area would be 4. It would be more than 2. Whereas in this example, on the scale of the original 2 functions, the resulting function looks wrong for some reason.
Yeah. So that's because both of these functions are less than 1. So you're multiplying 2 numbers less than 1, and you get. But ignore the normalization. That we can fix by throwing in a number. That's the easy part, right? And yes, we are doing all of this to help us extract features from our signal, and we'll see how. It's not feature engineering. We are just going to help the network this way. Yeah? And just a second. Online, if you have questions, let us know in the chat. We will answer. Yes?
Sir, can you explain again how the T gets defined, like the actual shifting?
T is every value from minus infinity to plus infinity. So you pick it, you pick a value of your T, and
So you select like a step size almost, yeah?
yes, we will get to the discretized version, and that's exactly what you do. We will get there in a second. No question from online? All right. So more examples. Now, how do we actually code this up? When we want to code it, we keep the function f at my mth point, and then the function g. These are all discrete functions, and then I define a step size and discrete step sizes, and I shift them by those quantas, and then I do a summation instead of integral. And that's it. That's the definition of convolution in 1 dimensions. All right? Now, how do we actually do it in Python? In SciPy, you have scipy.signal.convolve. That works for 1-dimensional convolution. You have different ways of doing it, different libraries. This works really well. And then for 2 dimensions, you have SciPy signal convolution 2D. And also you have ND image, where you have some predefined kernels that you can use. I'll show you examples of that. Hands-on. Let's see what we are going to do in the hands-on. We want to pick a square pulse, a top hat function like this. All right? And you will define it in Python in a way that it's 0 everywhere except between 100 and 200, where it is 1. All right? Then we will define a kernel that is a smoothing kernel. And for this one, we are going to use the Hann kernel. I'll show you how to use it. And here, scipy.signal.hann, between 0 and 50. So you say Hann 50, that defines the function for you between 0 and 50. All right? And then we want to convolve the square pulse with this. What does it do? After you do it, you'll see that it takes your square pulse, and because the maximum of both of them are 1, it doesn't change the normalization. So that's the answer to the normalization concern. It just makes the edges. So here you have sharp edges, right? You convolve it by this. It tapers off the edges, and it smooths the edges for you. Okay? And so you will do it hands-on. You'll see how it works. Then we will repeat the exercise. So this was in SciPy. We will repeat it in PyTorch. How does it work in PyTorch? In PyTorch, we have torch.conv1d, and you will give it the original signal and the kernel, and also padding. Just keep padding equals 5. I'll tell you what it is later. We'll talk about it. That's how you use it in PyTorch. What else can we do with it? There is another exercise here where you start with a noisy, so you generate a noisy function, white noise function, or a Gaussian noise function. How do you define a Gaussian random function in PyTorch? Who remembers?
Random.
Yes, torch.random. So you define the blue function, and this is a super noisy function. Then what we do is that we will take the kernel to be a constant function, just equals 1, between 0 and 10. All right? Just like that. And then we convolve this with that. What it does is, if you think about it, you take this function, multiply it by by 1, and then sum it up. All right. So what you're doing is actually you're binning it between 0 and 10. You're you know what binning is? You're averaging it between 0 and 10, and you're getting one number, and then you slide it 1 unit, and then you do the same thing. So you're averaging between 1 and 11, and then you put it here, and then you'll see that when you do this, this actually cancels out the noise, because this is a Gaussian noise centered at 0, and you'll get a smoother function as a result. And we will do this in PyTorch. And here is the answer. Don't look at it. Try it first. And plot it. So let's do that. Let's make sure that we know how to do convolution in one dimension, and we understand what convolution does, what is the kernel, and how changing a kernel changes what we do to our function. All right? There is another optional part. Don't do that part now. Do it at home if you like.